Hello student, good morning to everybody. How are you? I hope you all are happy, healthy and very fine at home. So what did we discuss yesterday? Yesterday we have discussed about the stereochemistry for SN2 reaction, means inversion of configuration. The stereochemistry for SN2 reaction is found to be inversion, and that inversion, how that there are the different proof or evidences. So far we have seen there are the different possibilities of how does the nucleophile attack, front side attack, back side attack, then different possibilities are there. There we have seen one experimental proof for the inversion of configuration. Second one, we have learned the experimental evidence for the inversion of configuration without breaking the bond between the chiral center. We converted first into its particular bad leaving group is converted into as a good leaving group, and then attack by weak nucleophile, then departure of the tosylate group, and that tosylate group is a very good leaving group because, or excellent leaving group, because this will be stabilized due to the resonance effect by S double bond O group. And in the second step, again when nucleophile attacking, as we know that it is approaching from the back side, and then there is a inversion of product takes place, and after the hydrolysis we obtain the product, it's enantiomer. And as we know that enantiomer means what? They are non-superimposable mirror images of each other, but only they differ only in their rotation, the equal and opposite rotation. One rotating the plane of polarization to right hand side, another one is rotated to the left hand side. So that type of the process is known, or that type of the stereoisomer is known as enantiomers that we have seen. Now is let us see as a third proof for the evidence for A, B, C, D, you can call it as here. Here the experimental evidence, experimental evidence for inversion of configuration, right? Now this is a last example which proves the inversion for configuration for the SN2 reaction. So in a previous example, what we did or what we saw, there we converted the substrate into its enantiomers in a 3-step. Here we are going to convert the substrate into its enantiomer in a single step. Let us see here the example. Here we are going to consider is this one, that is I think R2 octane. Here maybe as a plus, or plus you can call it R plus 2 octane. That is the example we are going to discuss here. Now again 2 octane, as we know that there are the 8 carbon atom in the straight chain, whereas 2 indicate the position of the iodine group, and R is a configuration of that substrate, right? So let us see again here. So octane means here like this, CH3, CH, here is the iodine group, and rest of the thing CH2, 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 1, 2, 3, 4, 5, 6, then 7, and this is a 8, right? 1, 2, 3, 4, 5, 6, 7, and 8. So this is the organic compound. Name of this compound is 2-iodo-octane. Now, can you tell me how many chiral centers are present here? Only one chiral center is present. Look at here. This carbon atom attached to 4 different groups. One is a hydrogen, one is iodine, one is a methyl group, and one is this one big group, right? As we know that. Now, so I am representing here this iodine and one of the methyl group, carbon atom and this iodine, they are in a same plane showing by normal line, as we know that. Now the hydrogen atom, as usual, we can show below the plane and shown by dotted line. Now this big group, we know that it is coming towards us and it is shown by thick lines here like this. So there are how many carbon atoms? C6 and H13, as we know that. 1, 2, 3, 4, 5 and 6. There are 6 carbon atoms, and count the number of hydrogen atoms, you will find there will be a 13. So therefore this is C6, H13. Now this is hydrolyzed. The name of this compound is a R. Why R again? Let us see iodine. Here is a iodine. Now if you see the atomic number of 4 groups attached to this chiral center, you will find iodine has a highest atomic number 128 is there, and therefore it will get first priority, then second one this, and this is a third one. Then the last one is a hydrogen atom, because hydrogen atom is the smallest one, and therefore 1, 2, 2, 3. What type of the rotation it is? It is a right hand side rotation, means dextrorotator, and therefore it is denoted by R, then plus dextrorotatory to indicate that 2 position of iodine, 2-iodo-octane. 2-iodo-octane. This is a name of it. Now this substrate, this is a optically active. Why optically active? Because it has a chiral center, and all chiral center are optically active in nature. The instrument used to measure the optical activity is a polarimeter, right? And therefore this is optically active in nature. Now there is this one labeled iodide 128, labeled iodide is here. So, and as we know that it is a heavier than normal iodine. Normal iodine is 128. It is a heavier element. It is known as a labeled iodide. This is known as labeled iodide. This is the experiment carried out. During that, what is happening? This is a nucleophile, and this nucleophile approaches from the back side. There is a departure of this iodine, and you are going to get the transition state over here, I128 ... this bond is going to form ... iodine is going to depart, and this methyl group I am showing over here, this hydrogen atom here, and this what we can call it as this group C6H13, and this is as we know that this is a transition state. As we know that transition state has sp2 hybridization, and substrate has sp3 hybridization, negative charge you can put here, or you can put minus 1/2 128 minus 1/2 iodine delta, right? And then this is a rate determining step, RDS, rate determining step. Only single step is there, and this single step is nothing but as a SN2 reaction. In a SN2 reaction, as we know that the nucleophile approaching the backside and the resulting compound we are getting in this case is this one, I128, then C, the methyl group is like this, CH-3, and then one of the hydrogen atom will be like this, and another group which is this one, C6H13. If you see its configuration again, it is 1, the priority number 1, this is a second one, third one, and fourth one, 1, 2, 3. So what do you see over here? This is a anti-clockwise rotation, and therefore it has S configuration, and S configuration there is a minus 2 iodo-octane. So that is a, see here, observe this reaction again carefully. What is our starting material or substrate, or the reactant has R configuration. When product is formed, that product will be the S configuration, and in this case what is happening, there is a racemization takes place here. Racemization, as we know that there are the two mixtures in equal amounts, and the whatever mixture is formed, that mixture is known as a racemic mixture. Here this is a starting substrate and this is the end product. They are in a equal proportion, and that's why they one rotating the plane of polarization to the right hand side, another one rotating to the left hand side, and there will be a racemic mixture. And here the racemization found to be a twice racemization. Means twice racemization means whenever the reaction occurs, the whatever product is formed, that product cancel the rotation of 2 moles of the starting compound, and that's why it found to be the twice is a racemization in this case. So I think with this we have completed all the evidences for the inversion of configuration, or in this way we have completed as a first part of this chapter. Means we started with that SN2 reaction. What is SN2 reaction? With the following point we have learned. Number 1 is what is that? Rate of reaction. Study of rate of reaction, we found that it is a biomolecular reaction because rate is depending upon the concentration of the substrate as well as nucleophile, and therefore it is a biomolecular reaction. After that, proposed mechanism, why backside attack or the nucleophile attack, then I think transition state, and after that energy profile diagram, and after the energy profile diagram we have learned as a stereochemistry for SN2 reaction, and we will find that here there is a inversion of configuration, and there are the some of the evidences. There are how does the nucleophile approaches. The nucleophile approaches from a different way, backside attack, front side attack. Why backside attack is a favorable, why front side attack is a difficult or a remote one. Then we have seen with the experimental proof, experimental evidences in a 3-step as well as in a single step. In this way we have completed all the point regarding as a SN2 reaction tomorrow we will learn the SN1 mechanism, there the SN1 reaction, how what type, and in a SN2 reaction it is a single step reaction. It is a concerted reaction. Concerted reaction means what? The breaking of bond and the making of bond taking place simultaneously, and that's why it is known as a concerted reaction. And the stereochemistry is always found to be the inversion in configuration, and these are the key points remember while studying the SN2 reaction. So I think with this, let us stop today here. Remaining we will see the next lecture. Thank you. Have a nice day.